Hello, my name is Stan Szymanowicz, and I will tell you about our paper X-Man, explaining multiple sources of anomalies in video. Our aim is to look at video and spot frames where something unusual is happening, and automatically explain what is unusual about it. For example, in a video like this, our aim is to spot anomalous behavior and explain that the anomaly is due to people pushing each other. Other examples of anomalies can include people picking up bags, people throwing bags, or people fighting. Anomaly detection has important applications in video surveillance. However, in public settings, we believe that explanations are absolutely essential because the systems have to be transparent in order to prevent any bias, for example, racial bias, and the appropriate response depends on the nature and severity of the anomaly. Explainable anomaly detection is difficult because deep neural networks at the forefront of this problem are not interpretable. There is also little labeled data of anomalous events, and the most important anomalies involve complex interactions between people and between people and objects. To the best of our knowledge, there's only one work tackling the task of describing the detected anomaly. The shortcoming of this approach is neglecting the interaction between objects, and that approach is still not fully explainable, i.e., the input features for detecting anomalies cannot be inspected. Due to the lack of training data, there are also difficulties in forming a benchmark on the task of anomaly explanation. Other recent methods for anomaly detection use deep feature representations and are not interpretable. To address these shortcomings, our work builds a new dataset for the task of anomaly explanation, which show how to build interpretable features and use them in an explainable anomaly detector, and we are the first ones to use interactions explicitly to detect anomalies. We build a new dataset X-Man. To produce labels, we take frames from existing datasets and label them with a description of the anomalous event. The label consists of two tags, a coarse explanation. Is the anomaly due to an anomalous object, action, or an unusual location? And a second tag, fine-grained description, for example, running. The whole dataset consists of over 40,000 such labels in over 20,000 frames. Here is a part of our demo video where you can see more examples of X-Man labels. The labels from the X-Man dataset are shown in the top left-hand corner. To detect and explain anomalies, we take an input frame, detect all objects in the scene, and detect anomalies by building a human-object interaction vector for each pair of objects in the scene. The Howey vector is inferred using deep neural networks, and for more details, please refer to our paper. We can then interpret the anomaly by direct inspection of the Howey vector. We can also explain the anomaly by identifying which of the three parts of the Howey vector was anomalous. Was it the interaction, the object, or the location? In this case, it is a bicycle, the object, because we have not seen any bicycles in normal training videos. In more detail, in training, we build a Gaussian mixture model of normal events represented by Howey vectors from the training frames. In testing, we declare a frame as anomalous if at least one of its Howey vectors has low probability out under the Gaussian mixture model. We can then interpret the anomaly by direct inspection of the Howey vector and explain it by retrieving the closest normal events, and by measuring the Mahalanobis distance in the Gaussian mixture model, we can identify the elements of the Howey vector that made it anomalous. In this case, the anomaly is due to an anomalous object, a bicycle. Here are some examples of correct detections of anomalies and the explanations provided by our system in three different anomaly detection datasets. The boxed areas show a human object pair identified as anomalous. The red box in the top right corner indicates the salient feature causing the event to be detected as anomalous. We find that we perform on par with state-of-the-art on the task of anomaly detection. We believe a slightly lower performance is not a problem because we are the only method providing full explanations of anomaly detection decisions. In a practical setting, this is advantageous because our system is transparent and allows for appropriate response to the detected anomaly. We find that the scores on the task of anomaly explanation improve where we use the interaction part of the Howey vector, which shows that interactions are important for explaining anomalies. Thank you very much for listening. For more details, please see our project page.